So we're doing revision today, but I mean, what particular parts of observable do you want to go through?
I have a few questions.
Oh, okay.
Like for the observable part is like its namesake. Are we given a pair, like a pair of, for example, in the cubic example, are we given like a pair of 0 and 1, and we're trying to determine its probability and using our observation to try to change the basis and then determine the probability as a whole.
I'm just trying to understand your question a bit. So
I'm confused.
Okay.
So basically, what are we what do we have in this observable, and then
I see. Okay. So probably I think the part about the measurement, I think you're probably fine with, right? Like you have this. Somebody worked the keyboard. Maybe you did it last week, right? So, I mean, probably this part you're fine with. Alright. So you have a state, and say it's a qubit, and then probabilistically it collapses to 0 or 1, and then the probability is the mod squared, right? So I take it you're fine with that part, right? And then, so maybe is the part that you're asking about is like sort of how that relates to observables, or?
Yeah.
Yeah.
Is it just we change the basis in observable?
So an observable has, it could be in any basis, actually. So basically, whenever you have such an observable, maybe, I didn't quite spell it out, but so basically observable has kind of like two parts to it, really. It has the, I don't know if equals is the right thing to say, but there's the measurement and the basis. So this would be like, in this case, the states n, right? And then there's the values for each outcome. So and then in this case, that's Qn. So there's kind of like two parts to an observable, and maybe the way that it differs from just the measurement is that it has these particular values that are assigned to each outcome. And I mean, this is kind of actually the usual story, even just with regular probability theory, because say you have like a histogram of people's, the number of people versus the height or something like that, right? So that you have some histogram like this, and so this height is basically what we're talking about, the value of the observable, right? So and then the number of people, of course, from that you can work out like the probability, and then from the probability you can calculate things like average height, or the variance of the height, or something like this, right? So the kind of the new thing that is coming in with the observable is really just this fact that we've got values that are assigned to each particular outcome. So that could be anything, it could have any units, like, it could be like the height, or it could be, the example that we had here was like the position of the box, right? So it's in this quantum state across many of these boxes, and there's some probability that this could emerge in, but kind of the new thing that we're doing here is we're just assigning like a value for each box, right? Because in this case, the boxes are laid out, in a line like this, and then we can talk about the position of each box, right?
Yeah. So I figure I didn't understand observable the first time. I thought it was change of basis and only observing this is not. So I got it.
Okay.
Yeah, now I understand.
Yes. So there is a basis kind of involved here because we're dealing with quantum mechanics, and so the measurement could be done in all kinds of different bases, right? So here we did a measurement in the 0-1 basis, but we could have done a different measurement, so for example, in the plus-minus basis, if we did a measurement here, then we get the probability of this plus state happening. I think we've worked it out several times now, so I'll just write the answer down here, but A minus B over 2, like this, right? So depending on what kind of measurement you're doing, you'll have a different observable, because if you're doing a different measurement, like plus minus versus 0, then you're going to get completely different probabilities. And of course, if you have different probabilities, you're going to get different kind of, averages and stuff like that. So there is the basis. Basis is important in quantum mechanics, but that, we already talked about actually before this set. And kind of the new aspect here is that we've got these values that we're averaging over, and kind of the main formula, if you like, of this whole set is actually this one. So we can combine these two things and make observable operator. So we basically kind of combine these two aspects, and then if we do that, then what is quite neat is that you can work out all things like averages in a kind of a very simple sort of way, which is just to so the average value of this observable that we just made up is actually what you do is something like this. So you have your state, you have your observable operator, and then you have your conjugate state. You just work out this, and this is basically like something like a matrix multiplication like this. So this is a row vector, this is a matrix, and this is a column vector. So this is state Q, state, conjugate vector. And then once you do that, you work out what this thing here is. You might think, well, that's just sort of a mathematical sort of way of evaluating it, and that's nice for theorists, but for guys in the lab who are actually doing this, what they actually do is really much more like this. So they're not doing anything like multiplying matrices or anything. But what they're actually doing is they're getting their quantum state, they're measuring it lots and lots of times, they get statistics, some histogram like this, they work out the probabilities, and then they just weight the probabilities according to these values in order to get the average. So that's what they actually do. So what they do in the lab is much more like close to the definition, but for us theorists, creating this operator and then doing this is quite convenient because you can just sort of put it in the formula and just calculate stuff easily.
Professor, a certain rule for us to determine how we assign a value to a common state. Like we assign the value -1 to the 0 state. So why don't we assign like 0 to the 0 state?
Yeah. That's just yeah. It's totally up to you actually. So there are sort of conventions and what a lot of people do or kind of common things, but in terms of how you assign these values, you can do that whatever you like because like my first example was like these boxes and that's a pretty arbitrary example, but this observable can have kind of any units. So this one, there was units of meters or something like that, but if I was measuring some other quantity, it could have any other units. If I'm measuring momentum, then it could be units of momentum or whatever. Energy would be in joules, and these numbers can be big or small. 0, they're observable, so they should be real numbers. Yeah. So yeah.
Like in the Pauli operator, we should assign like -1 and +1.
Yeah.
Yeah, but in other operators, the rules is depend on. I'm not sure. So we set the rule ourselves.
For observables, I think you can set these rules yourself. So these Pauli operators, this is kind of a convention, and eventually why it's chosen in this way, I think, is so that eventually when we work out like the expectation values for a qubit, then it comes out nicely, and then so you've got to choose your Pauli operators with that plus minus convention, and then you've got to parameterize your state in this way, and then if you do both of those things, everything comes out beautifully, and then it's all parameters of a sphere, right? But if you didn't do that, then I don't think you would get exactly that answer, and it would be less clear that it would be, that you could think of it in this way. So for the Pauli operators, it's just quite a common kind of way of choosing it, and I mean it has sort of some sense to it because essentially it's like how different the 0 weight is to the 1 weight. So it's if you've got more of the A or alpha here, then it's positive, and it's more beta, then it's negative, right? And if they're equal, then it's 0. So it's kind of like it's quite a common type of way of kind of determining. It's like a balance, right? So it's basically it's positive or negative depending on which one is bigger, right? So it's kind of a reasonable thing to do, but you don't have to do that. You could define your Pauli operator in any other way. Probably the only thing that you probably don't want to do is just assign them the equal value, because if you assign them the equal value, then basically it would always be equal to alpha squared plus beta squared. Well, okay, so if I assigned, let's call it not Z, but I don't know, W. So if I assign W observable, the same value like this, right? Then if I calculate the expectation value of W, then it's going to turn out to be 3003 A to B, and this will, you do your matrix multiplication, and this will turn out to be 3A squared B squared, but this is 1. So this thing will always be 3 no matter what. Basically, it's because this thing is actually 3i. It's proportional to the identity. And if you make it the identity, then basically you don't see anything about the state. But so long as you choose anything other than this, you will probably have some dependence on alpha and beta, so you will get different values for different states. But yeah, you can choose it as you like.
And can you explain what does the variance means in the real world?
In the real world? Well, I mean, I guess I'm pretty sure you know what variance means in the real world in terms of probability distributions. Square root is basically how wide this distribution is. Well, okay, this one doesn't look very like anything like a Gaussian, but basically, if you have a large variance, then well, okay, maybe this would be a more classic example in terms of regular probability. If you have a large variance, usually people's heights are not, wildly different numbers. They're kind of grouped, somewhere between 150 centimeters to maybe, 190. Like most people are going to fit in that range. Different countries will have different ranges, and so sigma, which is your square root of the variance, will be basically like how wide your distribution is. So it should be something like the width of this distribution. So in terms of quantum mechanics, what this basically means in terms of, okay, well, we can do a little example here of calculating the variance of the Z operator, Pauli Z operator, and so that means Z squared minus average of Z squared, and so we can do our matrix multiplication for this state. We can work out what Z squared is here. And if you do that, so what you'll notice is actually it's 1, 1 along the diagonal. Actually, so Pauli operator squared is actually equal to identity, turns out. So obviously this will do nothing to this state. So actually average of Z squared is an example where it's completely invariant. And well, okay, sorry. Let me do this one by one. So average of Z squared is going to be alpha squared plus beta squared, and that's going to be equal to 1. Okay, and variance is actually that minus average of Z, right? And so if you do that, average of Z, I think, is that written down somewhere? No. Okay, average of Z is so it's A star B, A minus B, and then so it's A squared minus B squared. So it's A squared minus B squared. Same and same. Okay, so our final answer is basically 1 minus another way to write this, because we know that alpha or beta squared is equal to 1 minus alpha squared. So put that into there, and we should get.
Isn't that a squared plus b squared?
Yeah, you're right. Yeah, I thought, yes. I was thinking there was something wrong there because it's going to get 1 or something. So if I substitute that into there, then I'll get 2 minus squared. Okay. So alpha is 1. I think I forgot to do something. I forgot to square this. Okay. Sorry. Let's do it again. Alright. And let's use so I think it's useful to do the Bloch sphere parametrization here. So if we do that, then we get this is so this is cosine squared theta over 2 minus sine squared theta over 2, and this is cosine of theta, right? So z is cosine of theta, so this is going to be cosine theta squared, and so this is going to be sine squared theta. Okay, I think now I should have it right. Yeah, okay, now it makes sense. Okay, and so what does this mean? So if you plot sine squared of theta, so this is what we're doing is we've got variance of z. So sine squared is 0 at 0, and at pi over 2 it's 1. So it does this. So basically it's the variance is 0 at 0 and pi, and it's maximum at pi over 2. And let's go back to the state and see if that makes sense. So in terms of our the Bloch sphere, our Bloch sphere parameterization was like this, right? So if theta equals to 0, then our state is actually just, get another color here. Our state is just 0 state, yeah? If theta equals to pi, up to whatever this phase is, our state is just 1. And if theta equals pi over 2, this thing is at something like 1 over root 2 of 0 plus e to the I phi 1. Right? So the variance is here 0, meaning that essentially in terms of our our observable z, if we do remember this z measure, what the z means is actually, the z observable means, so basically measure in the 0, 1 basis, and the values are -1 and 1, right? So if we're measuring in 0, 1 basis of this state 0, then we basically just always get 0, like 100% of the time. Yeah? So our probability distribution looks like So if our probability, we can plot our probability. There's only two values because we're just, just got a qubit. So for the state 0, for the state 1, basically our probability distribution looks like this. It's 100% 0 and 0% 1, right? And so whenever you get something where basically you're just getting the same outcome every single time, then the variance has to be 0 because basically there's no randomness kind of in the system, right? So in our height analogy, every person in the world is 160 centimeters. Then this, your histogram looks kind of like this. So there's no variance, right? And same with 1, right? So 1 would be that every single outcome is 1. For pi over 2, essentially you're getting 50-50, 0 and 1. In fact, so that's the most amount of variance that you can have. It's sort of, in a way, the most randomness that you're getting. So that's why the variance is the largest at pi over 2, because you've got an equal superposition of 0 and 1. So yeah, so basically variance means with respect to whatever measurement you're making, if you're getting kind of a large amount of variance, then your variance will be large. If you're just getting the same measurement outcome every single time, then your variance will be small.
So if we know the expectations and the variance of a certain observable,
Yep.
will determine its quantum state.
Yeah, that's a good point. No, actually. I think, say, from only these two values. So here we worked out that average of z was cosine theta, right? And then we worked out that the variance was sine squared theta, right? So first thing you notice is that there's no phi in there at all, right? So actually, this z doesn't give any information about this phi variable. So it's completely blind to that. So already you can see that it's not giving complete information about the state because we don't get that. But even if it wasn't that, essentially the average and the variance will just give you kind of two numbers here, right, in the probability distribution. And so for a qubit, it's kind of maybe reasonable that maybe two numbers might determine the state. So if somehow this other one was dependent on phi, for a qubit, and if it was a pure state, we're not doing mixed states in this course, but for a pure state, there's only two parameters and two equations, so you could work it out. But it just so happens that for this one, you don't get anything about phi, so in a way, you kind of miss out on that information. So for this case, you don't. So you need to do another measurement, like an X measurement or a Y measurement, in order to get some information about this phi. But yeah, I mean, for a qubit, potentially two numbers could, well, even one number could characterize the distribution because it's normalized, it's probability. So, in a sense, you only need sort of one number to characterize a two-outcome distribution, right? But if you had a bigger quantum system, like 10 levels or something like that, then basically there's no way that could characterize the state because it would not be able to characterize the probability distribution. So for a 10-level system, 10 outcome probability distribution, you need 9 variables to characterize it. Right? So this only gives you 2. So definitely it was not characterized. Okay. Okay, but I think we're getting actually even deeper than what we're doing in the lectures here. So in terms, you're probably more worried about your midterm, and I'm not going to, ask you some super deep questions in the exam. It's going to be more like kind of what you've done in the homework. What you said something about other measurements, or maybe that more or less answered your confusion.
Yeah.
Observable.
I think for the observable part, I understand more.
Okay.
There's another question about the measurement of another basis. I always thought if we changed if we change the quantum state into another basis, then we just use the coefficient in front of the other state. We just use that squared as the probability. Is that?
Yep, that's right. Yeah.
So is that consistent with the formula, like the P equals phi times m? How's that? A joint? Is that the
You mean
small t? Dagger.
Yeah, emission conjugate. Yeah, the DAG. Yeah. You mean the measurement operator, this one, and then the new state after measurement is these two forms, right?
Yeah. For the Pn, is that just like the coefficient for the n state squared?
Yes.
Okay.
Yes. So you can always use that rule of you just take the absolute values squared of the coefficient. So in fact, that's usually maybe simpler actually. Yeah. So if you get a question where it says calculate the probabilities, and it doesn't say use the measurement operator, then just do the simpler one. But yes, it's always consistent with that. The way of just reading off the coefficients and taking absolute value squared, of course, you have to do a basis transformation of the state first. So there is that work involved. Whereas when you do it with this one, you don't have to do the basis transformation of the state because the measurement operator should already take that into account.
Yeah, the problem with this is when I did my homework, I think it was homework 6. I couldn't computate the state of on the measurement because
because it was.
I tried to first do a change of basis on the state and then put the state back in. So we are not supposed to.
That's right.
So that's what the measurement operator is for. So we don't need to.
Yes. Exactly. Yeah. So I think I remember seeing your one, and I forget. I'm not sure. Was it just only because you changed the state? I mean, was the measurement operator? I think because you were working with the matrix kind of way. Another source of potential error is that you can maybe not get the right measurement operator because I think maybe the question was like.
Yeah, what's the measurement operator for plus what, like the.
Yeah, plus y.
Plus and minus.
So I think it's this, right? So, and then minus y is. Oh, and just sorry, just to before I rub this out. So in the latest homework, I think there was a question like work out the average values using
Yeah.
Sorry, just the average value formula, or use it using the probabilities. Basically, all I wanted you to do there actually was, so when I say work it out using probabilities, because all these Pauli operators are defined with respect to basically all these Pauli operators are defined in the same way. It's just like P0 minus like P1. So basically all you have to do for Pauli operators is to just subtract the two probabilities. It's because, so, it's because, where is it? Right, yeah. It's because basically, for each of these Z, X, and Y, one of the outcomes is assigned plus, right? And one is assigned minus, right? So the value is plus or minus. And then, so all you have to do each time is like work out probabilities. And then, the value of this one is plus, and the value of this one is minus. So it's just the probability, 0 minus probability 1, right? And I've written this for Z, but this is true for X or Y. So if you measure in the X basis, work out the probabilities of P plus, P minus, you just have to subtract P plus minus P, the other one.
So that's the meaning of the
Yeah, that's basically all I was getting at. So if you've worked out the probabilities, all you have to do is subtract them, and then that's the answer. Or what I was trying to get you to do in the homework was to just do that, or just evaluate the averages in a similar way to this, which I think maybe you all did that fine. Okay. Anyway, so getting back to the measurement operator stuff. So the measurement operator, so for the, say the plus y, is just defined as plus y up here. And so, where you can potentially go wrong is that this has got an I in there, so you might, sorry, made a mistake myself. No, that's right. So I just wrote it the wrong way. Okay. So in terms of matrix notation, we have to write it like 1i. Yeah. And the conjugate vector, it's the transpose and then the complex conjugate. So this will need to be 1 minus I. So this will be a half, and then you just do the matrix multiplication. That's 1 minus I plus 1.
Yeah, no wonder my calculations were wrong. I reversed the order of the two vectors. I put the transpose in front and then.
Oh. Right.
Yeah, that's also.
That's all. Okay. Yeah. I seem to remember that you might have done the inverse transformation, or is it actually just this one? Because what was the question? To remember what the question is. This was homework 6.
Question 3.
did it the measurement operator method, right? So, what's the state? State is that. Okay, so, so if we're doing a measurement operator method, then the probabilities are just like this. And so what we want to do is just apply this to the state. So 1 over root 2 state is 1 and here the I 5. So it's 1 over 2 root 2 of 1 minus I e to the phi and I plus e to the I phi. What was the answer? Does anybody have the answer? Oh, right. Well, we haven't done the probabilities yet, but okay. And then the probability is just that. So you just work out the conjugate vector of that one and multiply it by itself. Out. 1 over 8, 1 plus e to the I minus I phi, and minus I plus e to the minus I phi. Okay, so there's 4 ones. 4 and minus 2I the phi, and there's 2 of these ones. Then these ones. So this should be sine 2 sine phi. So they subtract, right? By, yeah. And so this should be a half of 1 minus sine phi. So yeah, I can put these homework solutions up. On NYU classes, so hopefully. Can't find it. It's not there. Got one plus, is it? Oh no. Yeah. This is cosine phi plus I sine phi over here, right? So minus I gives plus I, so yeah, sorry, this should be yeah. And yeah, 1 plus sine phi is the right answer. Okay, so yeah, right at the end there. But yeah, so you can do it like that. A little bit of algebra. Again, possibly in this way, it's probably easier just to do a basis rotation on the state. But yeah, but the point is that if you do this, then the state remains the same, and the measurement basis should be all contained in the measurement operator. Okay.
Can you explain the question number 4? It says that distinguish one state from another state.
Distinguish one, yeah. Well, okay, so why don't we look on the slides for that, and I can recap that first. The distinguishing something was...
This is in chapter 9.
Chapter 9, okay. Okay. Yeah, okay, so where should I start? Yeah, so for the purpose of this question, I think it's really just this one, this slide, and this slide that you need to understand. So, of course, if you have two different states, and in this scenario, I've got somebody that's sending me states which are either 0 or 1, and they're all going into my measurement device. And the task is that I need to be able to distinguish them, and because I don't know whether these things that are going to be arriving are 0 or 1, there's some other person over there that's sending these things, and it's like, I'm receiving some transmission of some data, basically, right? And so I need to be able to tell the difference between them, which in classical physics, it's obvious that you can do that because you do that all the time on the internet. But in quantum mechanics, it's not necessarily that you can distinguish them. So in this case, we need to actually put our measurement device in the right setting in order to achieve this, right? Because if obviously in the 0, 1 basis, and you're measuring 0, 1 states, then we can distinguish them. But even here, actually, if you choose the wrong basis in your measurement device, you're actually going to get, you're not going to be able to distinguish them properly because, for example, let's say you accidentally put your measurement device in the plus minus basis, right? So in that case, well, our measurement operators are going to be plus minus, so, and say you know, Alice or whoever's over there sends me that state, then the state 0, okay, we can just use the basis rewriting method because it's easier. Oops, minus. So if they're sending 0, then, and if my measurement device is in the wrong setting, then actually 50% of the time I'll get plus state, and then 50% of the time I'll get minus state. Simply because my setting was in the wrong setting, right? So even in this case, which looks completely classical, if these are quantum particles and you're doing quantum measurement, you can still mess it up and get like no information of what the 0 and 1 is. 0 or 1 is because you basically kind of got the wrong settings, right? So even in this case, you need to get the right settings. Likewise, so if the person is sending plus and minus, then you need to get the right measurement setting, and obviously the correct measurement setting is plus minus because they're sending plus minus states, and in that case you can perfectly distinguish between the two. So the question was, so say I would like to perfectly distinguish psi, which is this state up here, from the state plus, right? So the kind of the setup that I've got in mind here is a bit like what I drew in the slides here. So say I'm sending sort of randomly these states like this, right? And they're all going to my measurement device, which has got a nice knob here, which I can tune. So these states are all going there, it's all random, and I don't know if it's going to be psi or if it's going to be plus, right? So in order to distinguish these states perfectly, basically I kind of need these to be orthogonal to each other because, well, okay, so maybe I will explain the other slide there. So this was a case where I could still sort of distinguish the two states, but if I have a mixture of plus and zeros and minuses, then basically I can no longer distinguish these states anymore because these are not orthogonal states. So the thing that allowed me to distinguish the states was the fact that, okay, whether it's plus or minus or 0 or 1, these are orthogonal states, right? But now plus or minus, plus and minus are orthogonal, but it's not orthogonal to 1 or 0. Okay, so you need sort of orthogonal states in order to distinguish the states completely. And basically what this slide is arguing is that there's basically no measurement basis that you can do so that you can distinguish all 4 possible states. So essentially the key point here is that basically we need psi plus to be 0 in order for them to be distinguished properly. And as long as we can do that, then we can construct some measurement operators, and then we can have like the situation that we had at the beginning, where basically these two states were kind of perfectly distinguishable. So basically, you know, there's a little bit of sort of basically, you know, this is the key point that you need to have, and once you have that, it's just kind of maths to you know, work out what this condition here is. So psi is psi was 0 plus HDI phi. So the conjugate vector, so we need it to be e to the minus I phi, plus is defined as this. So this is 1 plus e to the minus I phi. That this needs to be 0, and so obviously this thing needs to be minus 1, and so you can just see from there that phi needs to be pi.
Is it possible to be 3 pi?
Oh, sure, yes, 3 pi, yes, sure. Yeah. Okay. Plus or minus 2 and pi. Okay.
So is that whenever we saw like whenever we are asked to distinguish two states, we just use the condition that we can only distinguish two orthogonal states, and then we like
Yeah.
get it done.
That's right, yeah. So if this was a slightly more complicated example, say that I didn't say plus, but I could have made this question a little bit more complicated and said distinguish it from the state, like you know, say let's call it theta or something, where theta is something like this, right? So say the question was a bit more complicated, but say I asked, you know, here are some states theta, what is the state phi such that it's distinguishable from this theta? In that case, basically procedure is exactly the same. It would be like this. Yeah, phi. And then here it's phi minus theta. And basically the only thing that really changes here is that phi minus theta needs to be pi. Okay, 2 and pi. So basically you need to choose an angle phi such that it's different from theta by pi. So, okay, that was a one parameter problem, but I could even make it more complicated by making it 2 parameters. But actually I think previously in the slides I showed you that if you've got any two states, like A was, no, I'll call it A, let's call it, I'm running out of Greek letters, chi is, well, let's use psi, as usual. If psi is A0 plus B1, then the state which is orthogonal to phi is always B star minus A star. And that always satisfies actually that equal to 0. So that appeared somewhere in the slides too. So I could equally use that formula because yeah.
And why do we need to measure it instead of telling the other person that you should measure in this state or that state? Is there a kind of communication protocol?
Yeah, no, I mean, that just completely depends upon the situation that you're thinking of. So you can have a situation where somebody has some, communication. They're allowed to call you up and do something. In this case, the idea is sort of more that there is no classical communication, not so much because of this problem of what I'm sort of showing here, but later on maybe when we talk about cryptography, essentially you don't want to announce anything over some public channel because that's kind of giving away information. So if you were telling everybody, like if you're phoning up Bob and you're telling them that hey, I'm going to send this stage plus and I'm going to send 0 now, or like I'm going to send, how do I get rid of this? Can't get rid of this. Okay, now we're rid of it. Okay, so if now I can't turn the page. Okay, so if I'm sending, if I'm telling Bob already that, it's sending plus minus basis, okay, now I'm sending in 0 basis now, or plus minus basis. If I'm doing that, then it's just about giving away the whole information about the system. And the idea is that you're trying to share something in secret from Alice to Bob. So I haven't really talked about it here, so don't worry for the purpose of the exam. But just in terms of the background, often the situation in something like this is that you don't want to tell the whole world what you're doing because you're trying to share some secret information.
But if we know how to measure this and how to determine the state, the measurement setting, then it will not be that securely.
Well, it turns out that you can build a secure kind of system like this. There has to be some initial calibration where you have to first agree that okay, so what is 0, what is plus and minus, and you agree on that. But after that, you can make something secure out of this.
Okay.
Anyway, we haven't done that yet, so we'll talk about that later, hopefully. Anything else want to go through? Yeah, so I'll upload the homework solutions and you wanted a copy of last year's exam, right? Yeah.
Yeah.
Yes.
Do we have a copy of last year's exam?
Well, of course I have a copy of last year's exams.
That would be great.
Yeah, so I'll upload that and yeah.
I have a formula table.
I think I will give you most formulas. I mean, there's almost no formulas though. What formulas are there? I mean, there's the formula for the expectation value. Okay, so there's this one, and there's this one. Something like this, or whatever that observable is.
Pauli operators?
Yeah. That. Yeah. I'll definitely give you that. Yes. And anything like sort of definition kind of stuff like that, like definitions of plus and minus states, stuff like that. Definitions, I don't think that you have to worry about because, I definitely need to give you that because if people use different definitions, then you get kind of the wrong answer. But yeah, I mean, in terms of formulas, I think there's not much more than this, and then there's the rule to square, absolute value square the probabilities. There's actually not so many formulas to remember, right?
Are we gonna have those like linear algebra stuff in the test? Like math.
I don't know. I haven't written the test yet, so probably not very much, even if there was. Nothing very complicated.
Yeah, that's right.
Yeah.
And do we need to bring a calculator or?
Yeah. Bring your calculator, and so just on the day, just put your bags and mobile phones and stuff away somewhere else, like just behind you.
Wait, we still have one class, right?
No.
The test. Oh, so the test is Tuesday.
Yeah, Tuesday, just during class. Yeah, and it should be I'll give you time for the whole class.
We'll cover chapter 12, which is the composite state.
Up to where we finished. So we haven't actually finished the whole.
So we won't cover this composite system.
Well, no, we finished up until something like we got up to somewhere like here, right? Measurement. Yeah, we didn't do that. Yeah, I don't think we even did that. I think we got up to here, right? Yeah. So,
That was like a math problem, actually.
well, simple math. Yeah, so just anything up until here. But, I mean, because you haven't really done much homework, you haven't really done the homework for this one, so, but yeah, in principle, anything up until here. Okay, all right, well, good luck. If you have any other questions, you can ask me in office hours. So I meet with my research group in room 1200 from 3 o'clock until 5 o'clock. So just come into the room and then.
Actually, it's over building.
Yeah.
3 to 4 in the afternoon.
3 to 5, yeah. Every day.
Every day.
Yeah. So you can just come in. If I'm talking to somebody, then just sit down and I'll get to you eventually. Yeah. Okay.